Okay, so far we've talked about equations that have only one variable. We used x mostly, but it could have been anything. But now we're branching out into having equations that have more than one variable. And we want to talk about very special equations that are considered to be what we call a function. Now, so far, um, when you see y equals something with x in it, there is a relationship between the x and the y value. And in this case, that relation will produce something called an ordered pair, and we always have them in order where the x value comes first and the y value comes last. And for what we're going to be doing, we're going to be talking about very special relations. And that is where if for every x value, there is only one y. I'm going to be redundant here. A single unique means that it is what it is and it can't be anything else. Y value. So for every value of x that we plug into a function, we have, sorry, hold on. If for every x there is only one single unique y value, then the relation that we are talking about is a function. Okay, functions are very special things. So I'm going to show you a couple of examples in the next page of what is and what is not a function. But you see with this example right here, if I plug in any particular x value, there's only going to be one y value that comes out. And the y value is going to be whatever I plugged in reduced by 3 units. See? And that's going to give me a relationship between a specific x value and its very own y, and there is no other y that can come from that x value. Now, sometimes things are functions when you can plug in two different x values and get the same y value. And that's okay because every x that I plug in, I only get one answer. It's okay if you get the same answer twice, okay? But for every x, there is only one y. You can plug in two different x's and get the same y, but you can't get two answers. That's what I'm talking about, all right? Okay, so far we've seen a linear equation. That is a function because for every x there is only one y. We saw a quadratic. That is a function because even though I can get the same y value for two different x's, say plus or minus 1, plug that in, it gets squared, it becomes positive 1, and you get negative 2 for both of those x's, but it is still a function, all right? What if I had y squared equals x squared minus 3? Now, anytime that you see an even power on the y, this is no longer a function. Because what do you have to do when you take the square root to solve for y? You have to say plus or minus, and that gives you two different answers. All right, so if you're having to decide whether an equation is a function or not, then that even power of y is a dead giveaway that it is not a function. Okay, so if I have a bunch of x's and I have a bunch of y's, we may have that each x goes to a unique y, or we may have that two different x's go to the same y. But as long as there are not two different arrows coming from the same x, then this is a function. Okay? Remember, each x has only a single y. So the x's are like monogamous and the y's sort of play around. Does that make sense? So this particular y may have come from two different x's. Say this was a +2 and this was a -2, and you squared them. You still get a +4. But you can't take an x and go to two different places and still be a function. This is the input. Okay. Now, if I had some x values and I have one x value going to two different y values, then that is not a function. Now, when we get later in the chapter and we start talking about inverse functions, then we're going to have something that's called a one-to-one function. In that case, you have every single x value in your domain, which we'll talk about in a minute, goes to only one y value, and every y value only has one x. So it goes both ways, and you get what's called a one-to-one function. Okay? 1 to 1. And we'll get more into that later. This is 1 to 1. This is not, because two different x's will give us the same y value. And if y is squared, it's not a function at all. Because, for example, what if y squared? Well, let's solve this equation for y. We have to take the square root of y squared, but we have to say plus or minus. That is the problem right there. I get two different y values for every single x that I plug in. So not a function. So what exactly is a function? We're going to write a function this way, and that's just the y value. But when we write it as a function, f of x, that's the way you read that, f of x equals y. It just means that this is like a machine where you're plugging in whatever the x's are, and you're doing some process to it. And you're chugging out an answer, okay? So x is the input and y is the output. And the function is the description of what's happening to the input. Function is the description, let's call it that, of what's happening. This is not a textbook way to write this, but it makes sense. Happening to the x value to produce the y. Okay, so in my case right here, My function f of x is cube it, square it and multiply it by 3 and add, multiply by 4 and subtract, and then add 2 at the end. And whatever the input is, whatever value gets done all of this stuff to it. Okay, so I can plug in numbers. Something cubed plus 3, something squared minus 4, something plus 2, and let's say that I want to find f of minus 2. Well, that means I'm plugging minus 2 wherever there is an x. All right? So all I have to do is chug out that answer, correct? So this is going to give me negative 8. When I square a negative, I get a positive. 3 times 4 is 12. Multiply a minus times a minus, I get a plus. Add them all together, and that gives me my y value when x is negative 2. So add these together, I get 14. That produces a point on the graph that is a picture of this relationship, this function. And we'll talk about what a graph of a function looks like in just a second. All right, so whatever your input is, you just chug it out and you get your output. Let's try something else here. Let's try f of minus x. Well, f says I'm going to cube it. I'm going to add 3 to the square of it. I'm going to multiply it by a minus 4, and I'm going to add a 2. If my input is some other function, we'll talk about composite functions later, but you see that we can do this. What do you get when you cube a negative? You get a negative. What do you get when you square a negative? You get a positive. Doesn't matter what x is, right? Minus a negative is plus, and I get a brand new function. Now in this case, I plugged in a function, so I don't get an ordered pair because it's not numbers. But you can plug anything you want into a function and chug out the answer. Let's do some more. Let's say that I have the function 1 over x minus 3. Let's say that I plug in a 5. That's 1 over 5 minus 3. You're just plugging it in, and you get an answer. Well, that means that if x is 5, y is 1/2. What about f of 3? Uh-oh. That does not exist, and that leads us to the next thing, the domain of a function. The domain of any function is all allowed or possible values of the input, and I'm just going to say x for now. Values of x. Let's make this better here. So you see for this problem up here, you can't divide by 0. So right from the beginning, you should have said x can't be 3. We've done this before in other problems, and I've used the word domain. This is what I'm talking about. It's the domain is all values of x that are allowed So the domain of this problem would be minus infinity to 3, and then 3 to infinity. But you see how I used interval notation to cut out that actual place where x is exactly 3. I can get infinitely close to 3 from this side and infinitely close to 3 from that side, but I can never touch it because you can't divide by 0. Okay? So, knowing the domain of a problem is a huge benefit right from the get-go, because you're not going to solve an equation and get a value that isn't even the domain of the problem. When we do rational problems, remember, with fractions in them, that can be an issue. You always have to check your domain, okay? Now, one last little bit about a domain. I want you to put this little tidbit in your brain and keep it forever, because it's going to make your life a lot easier when you start having to use this stuff. Polynomials have no domain restrictions. They are continuous and defined for all values of x. All right? Now, the domain is the allowed values of x, but the range represents all possible values of y. Or the output. Okay? Now, for the problem that we did up here, if I have one thing and I'm dividing it into pieces, divide it by any number, I'm never going to get a 0, right? So the range for this, and we're not going to get too deeply into this until we start graphing, but the range of this problem right here would be everything except 0. So I would write range is minus infinity to 0, stop, start again at 0, and go to infinity. All right? And that's how some of these problems will work. Now, polynomials have no domain restrictions, but that does not mean that they don't have a restriction on their range. Let's check one out on the next page. If y equals x squared is my function, my domain is all real numbers. Because it's a polynomial, I can plug in anything. But what about my range? Let's think about what this is. If I plug in a -1, I get a +1, right? If I plug in a minus anything, I'm going to get a positive number. That's for if c is, well, it's always positive, right? So anytime you square something, you get a positive number. If I plug in a 0, I'm going to get a 0. So obviously the closest that I can get to my range being negative is 0. So my range is going to be from 0. Oh, wait a second. I made a mistake. I can equal 0, can't I? From 0 and all the positive numbers. Because when you square a real number, you get a positive real number. When you square a 0, you get a 0. You're never going to go below 0 if you're squaring. So that's an example. And this is a function. It's a polynomial. You don't even have to check it. Okay? One last example. What about that? Well, you know your domain. You can't take the square root of a negative. So x has to be greater. Can you take a square root of 0? Well, 0 times 0 is 0, right? So the square root of 0 is 0. So my domain is 0 to infinity. What about my range? Well, remember when we were working these problems in the last chapter, if I give you a square root, it's either positive or negative. So this guy is the positive one. That means my range could start at 0 because I can take the square root of 0. It's in my domain. But my range is going to be also positive. If there had been a minus in front of this, this would have been minus infinity to 0. But it's the positive square root, so it stays positive.